Assalamu alaikum. Hello everyone. I hope everyone is doing very good. So today in this lecture, we will see about seepage. What is seepage? How it really works? Okay. So before the starting of the lecture, I would like to clear some basic concept from seepage. That is, seepage is basically related to soil structure of ground. Okay. So when any water flows above the ground, so basically when the water infiltrate through that ground surface, this term is called basically the seepage. That means the flowing of water into the ground is basically termed as seepage. So in introduction part, we will see the interaction between soils and percolating water is important. That means how the soil particles are attracting each other's and how the water is passing through the voids of that soil is very much important, especially for design of foundations and earth slopes. So when we design any foundations or when we need to settle any earth slopes, we need to know about the seepage conditions of that circumstances. Okay, so another term is to determine the the quantity of water lost by percolation through a dam or its subsoil. So how much water is passing through that portion by the percolation process is also important where we build a dam, okay, where the subsoil is present, because the more the seepage nearer by the dams, the more the losses will happen. Okay, so it's very important to know the seepage of that soil particles, whereas any big structures are uh, built up. So to determine the stability of slopes, the first thing is the stability of slopes. To determine the stability of slopes, calculation of seepage force is important. So we have to know the specific seepage force. So in this today's lecture, we will focus on the seepage force, how we can easily determine the seepage force. Okay, so the seepage is basically they're related to stability of slopes, foundations. Okay, so we have to determine the seepage force. So now we have to get into some empirical equations. We have to first determine the continuity Laplace equations. Okay, so here we can see this figure. Here there is a pile, sheet pile is driven. Here is a water layer, here is another water layer. Because of this sheet pile, the water can enter into this portion. So there is a little bit head difference. Okay, so this is a water layer and this is another water layer. So there some head difference happen. So now we have to take some small portion of the soil particles below this water table. So this small portion has a 3 dimension dx, dz, and dy. In this portion, dy. So if we consider it in 3D, it has 3 dimensions dx, dz, and dy. Now we have to see how much discharge velocity is going on and how much inflows are coming. So this basically uh, these two terms is known as inflow. Okay, the inflow through the soil particles, and these two terms is denoted as the velocity discharge. That means how much water is discharged. So before assuming these things, we have to assume another few things. Okay, for the applications of Laplace equations, we have to assume the flow is 2 dimensional. That means flow is going in 2 direction. One is this direction horizontally, another is vertical direction. The soil and the water and the soils are incompressible. That means this soil cannot be compressed. Okay, this soil cannot be compressed, as well as the water also. The soil is isotropic. This soil is isotropic and also homogeneous. That means there is no variety of soils. Only one type of soil is present here. The soil is fully saturated. That means the soil has surrounded by a water table. That's why this term is called fully saturated. The soil is steady, the flow conditions do not change with time. That means the flow is going in a fixed or with a constant velocity. That means the flow is steady. The Darcy's law is valid. That means we already know what is Darcy's law. In Darcy's law, we determine the velocity, okay, the discharge. So we can easily apply the Darcy's law for the Laplace equation. So we have to consider this six assumption if we want to develop Laplace equations or continuity equations. Yes. So we found this one after calculating some equations. We finally found this continuity equation that is called these things. Okay, so we have to remember these terms. Now we will see the simple flow problem. Now here there's a two kind of soil particle. One is soil one, another is soil two. So this soil has a total depth h1, and this soil particle has total depth h2. That are capital H1, capital H2. So now these soil particles have a pressure. That means from this water table to this soil water pressure is termed as H. So we have to determine actually the H, constant head. I mean, if we permit the water to infiltrate to these soil particles, how much pressures will be developed or how much head will it have? So we have to determine this H. So here another terms we have to know, that is from this water table to this water table, the height is h1. From this water table to this soil particle head is called h2. That means small letter h2. So this is small letter h1, small letter h2. This is capital H1 and this is capital H2. This is soil particle 1, this is soil particle 2. So this is the actual head, okay, for these types of soil. So this is basically the z. Z means the elevation. From this one we have to calculate. Okay, so now here we will find some equations for basically therefore for this condition. That means if z is greater than 0 and less than h1 or equal, h1 means this one. If this z is equals to h1 or this z is less than 0, then we have to apply these conditions. So we have to just keep in mind. So for another condition, that is if the z is greater than this h1, if z is less than h1 plus h2, then we will have another condition. Okay, so we have to just put this equation. So after calculating these equations, we finally compose it. Like for these conditions, we finally found these equations. Okay, here we can see the another term that was k1 k2. So there the coefficients have came, that one k1 k2. For soil 1 k1, for soil 2 we finally found k2. And also for this equation we similarly compose it to another equations, and finally we found these two equations. So for any mathematical problem, we just have to put down these equations to find the exact head, constant head. Okay, for simple flow problem. So we will just memorize this one. Okay, simply we will just memorize. If any mathematical problem will come on, then we will put the equations. Okay, so this is the equations for simple flow problem. Now coming into the deep knowledge, we will see what is flow line, potential line, and also flow net. This is a sheet pile driven, okay, so that the water can't enter into this portion. So this is upstream, this is downstream, and the difference between the water table is called head loss. So because of having some differences, this water sometimes will percolate through this region. Okay, the water will wants to percolate beneath the sheet pile. So here, what is called flow line? That means if the water percolates through this region, through the soil particles, okay, the path is called the flow line. So this is actually the flow line, not flow net. There the water is percolating. Okay, so this term is the path which the water percolates is called the flow line. And what is equipotential line? Equipotential line is the same head of water. Okay, that means if the water percolates, it's having the head there, it's having the head there, it's having the total head there. So all the same elevation of the head, if we connect all the head of the water, we will find the equipotential line. Okay, so we have to remember just the same head of water. So we are connecting the same head of water. So we will find here another one, another one. So this line is called basically the equipotential line. So what is flow net? Flow net, this flow line and this equipotential line both combines the flow net. So these two terms will known as flow net. So here we find the flow line, and here we find the equipotential line. And the thing is, this flow line and equipotential line intersect at 90°, and also it will create some squares. Okay, we will see in another figure. Here we see the impervious layer. So these terms are called flow line, equipotential line, and also the flow net. So how we can draw flow net? Draw a geometry of surface correctly on the paper. We have to take a paper and we have to draw the geometry. Select a proper NF values. NF means flow number. We have to see exactly how much flow number we will get. So this is number 1, number 2. This is flow number. It basically varies between 3, 4. Okay, for the first trial, if we want to draw a simple flow net, then we will just put 3 or 4. So identify the boundary flow line. Now we have to identify the boundary. I mean, it will be from here to here, or it will be from here to here. We have to first find the boundary. Okay, then also the equipotential line in the drawing, and also we have to find the boundary of the equipotential line in where we will draw it. In an example is given here, the upstream downward and the downstream ground surface are the initial and the final equipotential line respectively. Okay, so this is called the upstream, this is called the downstream. So connecting from upstream to downstream, the path line is called basically the equipotential line. The front and the back side of the sheet pile. This is the sheet pile, then this is the front side, and this is the back side. So the front and back side of the sheet piles and the surface of the impervious layer are boundary line of the flow line. So this is the front side, this is the back side, and this is the impervious layer. So these three, 1, 2, 3, these 3 layers will combinedly compose the flow line. So we are the upstream, here the connecting to impervious layer, and here the downstream. So these 3 layers will connect the flow line. That's why it's indicating like that. The 4th number is first draw trial flow lines with the selected NF. Now we have to draw the flow line. We suppose we took only NF equal to 4, then we have to draw 4. Okay, 1 line, 2 line, 3 line, then 4 line of the earth structure. This must be done based on the engineer's best instinct on how water flows. So basically the engineers will determine how much line we have to exactly draw based on the water flow. It should be noted that there are equal amount of water flow through all the flow channels. So it's actually assumed that the water flows will be equal in all the flow channel. Okay, so it will be equal. It won't stop here, it won't stop here. It will go through this layer and it will touches to this layer. By starting from the upstream side, so starting from this side, draw the first equipotential line. Now we already have drawn this first equipotential line to have all net openings. Squares are near, squares with 90° intersections. Okay, now we already have, this is the first equipotential line from the upstream side. This is the upstream side we already have drawn. So after drawing the flow line, so we see when we draw it, here we find the 90° intersection, here we find the 90° intersection. So we already have mentioned it. Continue the foregoing steps for the second and third equipotential line and so on. So now we have to draw another one. Now we have to draw another one. So we have to gradually draw 2, 3, 4 equipotential lines. So here we can see how much discharge, how much water will percolate to seepage. Here basically the flow line and equipotential line, they basically intersect at 90°. So here is the total depth L1, in this portion L2, in this portion L3. Okay, so the total net amount of water will percolate. So this region is del Q1, del Q2, del Q3, and this is the total del Q. Okay, so this is the height H1, H2, H3, and H4. So we basically found this flow net. From this flow net, we determine the equation Q equal to KH NF by ND. What is NF? Number of flow channel, and D is number of equipotential drop. So when I give any values of NF and ND, you have to use these equations to find the discharge. So you have to just remember the equations. Seepage thrown out the dam on the impervious days. Here we see a dam. This is basically a dam. We basically use the dam to prevent the water so that it can't percolate through this one. So this is a dam. So this is a dam. The water won't percolate. So the water table have the pressure through this region. If any water percolates, then this portion will be affected. So we draw a line, and from this portion to this portion be indicated as L. Okay, and this portion water table is indicated as H, and this width is indicated as D. That means this is from this portion from to this portion. Okay, this is indicated as D. Now we have to use that equations, and this is also called how much the slope it has, the dam alpha, and this portion the slope is beta. So how much seepage we will found if we construct a dam? We will we will literally found this equation. Okay, Q equal to KL tan alpha sin alpha. So what is the L? We have to use these equations to put the values of L. What is D? D is this width. Okay, this average width. Now cos alpha, we have to find the alpha. So we have to find the alpha. We have to calculate the del. What is del? This portion is called this, from this one to this one is called del, and this portion is called del. So we have to calculate the D. D means this one. We have to calculate the 0.3 del. We have to calculate this del. Now we have to know the value of alpha, D, and also we have to finally calculate the L. So after putting the value in this one, we will find the Q. So this equation is called basically Schaffernak solution. So if the alpha is less than 30 degree, then we will use this equation. So when we will find the alpha less than 30 degree, we will use Schaffernak solutions. When is greater than 30 degree, then we have to use Casagrande equation, that is L equal to this one. So we will put this value of L there, and we will finally find the seepage rate. Okay, so these are the equations of basically the seepage rate, how much seepage will be obtained. So now the important topic has risen, that is what will be the stress conditions. Without three conditions, we already know these graphs from the effective soil stress from the lecture basically 6. So we will all have some ideas from that lectures. Now we will just go through this one. So there basically you see the valve is closed, so there no water will comes or no water will goes. We have the water layer from this one. This is the soil, this is the soil particles started from A, this portion is C, and this portion is B. So we have to draw 4 stages. Okay, from 4 stages we have to see total stress, pore water pressure, and also effective stress. What is effective stress? We know if we deduct the pore water pressure from the total stress, we will find the effective stress. So how much the total stress we will find? There here you can see there is no seepage. Okay, so no seepage, that means no water is coming or going. So from this portion as it is the total is the height above, there is no total stress. When the height is coming, we will find some stress. Okay, so there is no height, no stress. We found the height h1 at point A. So at point A, the stress will be h1 gamma w. Why gamma w? Because this is totally full of water. So we have to put the gamma w. Now we have to draw for C part. Okay, for C part, we see the total height h1 plus z. So this is the height h1 plus z. How much will be the total stress? We already found h1 gamma w for this one. So this one will come, and also this one will come. And you have to use gamma saturated. Why? Because these soil particles have a water table above. So it will be gamma saturated, not gamma prime or not gamma w. So this C portion will have total stress like h1 gamma 1 plus z. That means this soil portion into the gamma saturated. Okay, so z gamma saturated, we already found that. Now for this portion, how much total stress we will find? So finally the total height is h1 plus this portion h2. So H1 plus H2. How much stress we will find? H1 gamma W, H1 gamma W plus this whole portion has gamma saturated. So H2 gamma saturated. So these are the total stresses. So how much the water pressure we will have? We have to see this layer also. For the A portion, this water have same height. For C portion, this water have same height. For B portion, this water have same height. But when we will go to another figure, upward seepage, this height will change. No seepage, we will find the same height. So for B portion, sorry, for 0, there is no height, so water pressure 0. For this portion, the water pressure will be same. H1 gamma W. This is actually the pore water pressure. H1 gamma 1. Okay. For C portion, we will find this height H1 Z, H1 plus Z, and we are calculating water pressure. So there will be only gamma W, gamma W. There will be no gamma set, no gamma prime. You have to just remember these things. So total height into gamma W. Now for this portion, total height H1 plus H2, and we will find into gamma W. So we already have put it this equations, okay, for water pressure. So how much will be the effective stress? We have to deduct this from this. So we will find 0. We have to deduct this one from this. Now we will find Z gamma bar. It's, see, this one is gone. Okay, so if we write gamma set minus gamma W, that is called gamma prime. Okay, submerged unit wide. This is called submerged unit wide. So we found the effective stress Z gamma prime. How much will be effective stress here? We have to deduct this one from this equation. So we will find, see, this one will go, and gamma set minus gamma W, that means gamma prime. So H2 gamma prime is the total effective stress. See, so we see from this one, from this one, the total effective stress has decreased basically. Okay, the total effective stress is decreased from, you see, from this portion it decreased to this portion. Now for upward seepage, that means the valve is open, the water is coming from downward to upward. The way so the seepage is coming from downward to upward. The water is percolating from downward to upward. So how much stress, effective stress we will find? See, for A portion, the height is same. For C portion, as the water is coming from downward, the high water table will also rise, and that means the head will also rise. So for C portion, we will find this height. Okay, this H by H2 is basically termed as I, hydraulic conductivity I. So Iz, we found Iz for C portion. Okay, Iz is increased. For B portion, basically total H, small letter H is increased. Okay, so basically we found this one, a small letter H. So how much effective stress we have to calculate? We have to calculate, see, this is the total stress. So I'm not describing it, we already found it. The total stress is same as above, described above, with no stress, without seepage. This one and these ones are same. So the change will be here, pore water pressure. So the in pore water pressure we see for this portion H1 gamma W, this is also same, but this portion is changed because the water height is changed at C point. So let's concentrate on C point. See what will be the pore water pressure. Let's consider from the upper portion. H1 gamma 1 will come. So H1 gamma 1 already come. So for Z1, for Z height, Z gamma W we have calculated. For this portion, we have to add this one. Okay, this is Iz. I already mentioned this is Iz. For C part, we see the water is increased from this to this. So this is Iz. So Iz is the height, and we have to multiply gamma W. Okay, so we already found the pore water pressure for C. So for B, what it will be? It is similar like C, how we calculated. C, H1 gamma 1 is uh, We will see you another day.